In 1927, Davisson and Germer, they were conducting an experiment to study the scattering of electrons. The experimental setup consists of an electron gun, an electron detector, and a nickel block. The beam of the electrons was incident on the nickel block, and based on classical physics, they were expecting the electrons to be scattered in all the directions. And yes, they did observe this with moderate dependence of the scattering intensity on the scattering angle and even less on the energy of the electron in the beam. After the experiment, an accident happened in the lab, and that changed the whole outcome of the experiment. This experiment turned out to be the proof of de Broglie hypothesis because of that particular accident. In this video, we will find out what that accident was and how it led to the proof of de Broglie hypothesis. In the middle of one of the attempts to do the experiment, an accident occurred that allowed the air to enter the apparatus and oxidize the metal surface. To reduce the oxide to pure nickel, the nickel block was placed in a hot oven, and after this treatment, the nickel block was returned to the apparatus and they resumed the experiment. Now, when they repeated the same experiment, the electrons were not scattered uniformly in all the directions. Instead of a continuous variation of scattered electron intensity with angle, distinct maxima and minima were observed, whose position depend on the electron energy. So to understand this, they plotted the polar graph of electron intensity. These are the three polar graphs from the experiment, but before talking about this graph, first let us try to understand what a polar graph is. The method of plotting in polar graph is such that the intensity at any angle is proportional to the distance of the curve at that angle from the point of scattering. So if suppose the intensity were same at all the scattering angle, then the curve will be a circle centered at the point of scattering. But if we look at these three graphs, none of the curves are circle. So the electrons are not scattered uniformly. And as we change the voltage, here changing voltage means we are changing the energy of the electron coming from the electron gun. So as we change the voltage, the scattering pattern is also changed. And at certain voltage, we can see then the maxima minima is occurring. That is, here at 54 volt, we can see that the maxima is occurring at 50 degree. So this pattern was something which was not expected because they were expecting the electrons to be scattered in all the direction. Here we have two important questions. First is, what is the reason for this new effect? Second, why did it not appear until after the nickel was back? And it turns out the nickel which was used before the accident, it had a polycrystalline structure. That is, it consists of many small crystals. Now on heating, these small crystals, they form a single large crystal structure where all the atoms are arranged in a regular lattice. Now, if we see the nickel target as an arrangement of atoms in a regular lattice, then it is like the electrons are scattered by the regular crystal structure and it is forming maxima and minima. And in the wave domain, we have a similar example, that is the X-ray diffraction, where when we incident an X-ray on a regular lattice, then maxima and minima appears, and this is governed by the Bragg's law. Now, if you compare these two examples, on the right hand side we have the wave phenomena, and on the left hand side we have an electron exhibiting a wave phenomena. And this is nothing but electrons are behaving like a wave. So Davisson Germer experiment is a qualitative proof that electrons can behave like a wave. If the electrons are behaving like a wave in Davisson Germer experiment, then we can calculate the wavelength by using the de Broglie's formula. So for a given kinetic energy of 54 electron volt, if we use these two formula, then lambda is 0.166 nanometer. Now for this given kinetic energy, it was found that the scattering angle is 65 degree and the separation of the lattice is 0.091 nanometer. And if we take the first order, then using the Bragg's formula, lambda is calculated to be 0.165 nanometer, which is very close to the wavelength predicted by de Broglie hypothesis. Now, we can conclude that it not only proves qualitatively, it also proves quantitatively that electron is behaving like a wave. And in summary, the Davisson Germer experiment verifies the de Broglie hypothesis. If you found this video helpful, don't forget to subscribe. And if you want me to cover more topics in physics, let me know in the comments.